Our previous work completed in detailed design has provided us with a suite of design artefacts that will support construction and production. We have detailed design documentation like drawings and software design documents, but we've also got detailed parts lists, material specifications and process specifications to explain how to produce and construct our system. In parallel with the preliminary and detailed design process, our production specialists and integrated logistics support specialists will have been working with our engineers to ensure that the design is, in fact, realisable. They'll be planning the production and construction effort in order to address key issues such as plant requirements and specialised equipment requirements. For example, in constructing our house, we might need to ensure that earth-moving equipment, concrete mixers, pumps and so on are available when we need them. The specialists will also be looking after long lead time items that are part of our design to ensure that these items are ordered in a timely fashion so that they're available when they're needed. For example, if our house design makes use of special material like imported tiles or floor coverings, we may need to order these items in sufficient quantities well in advance of the construction starting. We may need to store those items in a warehouse or a storage facility in sufficient quantities to support the build. Things like shelf life and storage conditions will then become a consideration. The construction planning will also need to take account of specialised human resources required during the construction. In our example, the list of specialists is long, from equipment operators, concreters, plumbers, gas fitters, carpenters, roofers, electricians, cabinet makers and so on. These human resources need to be organised to be available with the appropriate skills and experience at the appropriate time. This all takes planning and management. From a systems engineering perspective, the ability to influence the direction that the system is taking is now rapidly reducing. Making changes at this stage in the process will be very expensive indeed, if possible at all. Systems engineers are now generally more interested in confirming that the design, as specified, is in fact being realised. A major systems engineering task during this stage is to work towards system-level verification by confirming that the as-built system is meeting its specified requirements. We can do this in a variety of ways, but it's generally a combination of inspections, analyses, tests and demonstrations. Let's look at some examples of each. Inspections. If we needed to verify a given layout requirement had been met in our kitchen, we would probably simply inspect the kitchen to confirm this. Analysis. If we needed to verify that the electrical system was able to safely interface with mains power, we would want to confirm that the installed switchboard had been previously approved for this sort of task. We may do this by analysing the documentation and certificates that came with the switchboard used in our electrical system. Tests. If we wanted to confirm that the hot water at a certain temperature was delivered to every tap within X seconds of turning on the tap, we might use test equipment like a stopwatch and a thermometer, and an agreed test procedure to measure the time it took for hot water of a given temperature to be delivered. Note carefully that testing normally involves test equipment, measurement and data collection. Demonstration. If we wanted to check that all of the lights were working, a simple walk around and a demonstration of the lights might be sufficient. Configuration audits are also used to confirm that we have an accurate description of the as-built system. There are generally two types of audits conducted by systems engineers: functional audits and physical audits. A functional configuration audit makes heavy use of the verification results discussed previously to confirm that the system's functionality is accurately reflected in the system's documentation. By completing the functional configuration audit, we can be confident that our documentation accurately describes the function and performance levels of our system. A physical configuration audit confirms that the physical description of the system is consistent with the as-built item. This ensures that we are certain of things like materials and parts that have been used in the construction and layouts of things like interfaces. The critical point to note, especially with physical audits, is that they can often only be done during construction and production, not afterwards. For example, a physical audit of our house will confirm that the drawings of things like stormwater and sewage connections is accurate on the drawings. Really, the only way to do this is to walk around the block of land and confirm that the location of the pipes in the ground is as per the drawing. This needs to be done when the trenches are still open and an inspector can see that the pipes are in the ground. The inspector is then able to correlate what he or she sees on the ground and what he or she sees in the drawings. For example, here's an image of an established garden bed, under which lies stormwater drains. I recently needed to locate that stormwater drain so that I could finalise an irrigation system in my garden. If I was not certain of exactly where that stormwater pipe was, I would need to dig around in the garden until I found it. This digging would damage my established garden and potentially cost me a great deal of money to repair. Fortunately, when the house was being constructed, I walked around with the plumber and with the drawings and confirmed exactly where the pipes were laid. I was conducting a physical configuration audit of the plumbing. When it came time for me to locate those stormwater drains, I simply dug a hole exactly where the marked up drawing indicated, and there was the pipe. I was not surprised to find the pipe because I was certain of its location via my physical configuration audit. As we're progressing with construction and production, we'll start transitioning to the utilisation phase. This transition will require us to revisit those life cycle concepts that we established way back in conceptual design. This will help us transition the system to operational use by our stakeholders. Issues that will need to be finalised and activated will include things like the facilities that will house our system and its associated support system, the personnel who will use and support the system, any training systems that will need to be used to train our users and support personnel, the maintenance and engineering support systems, including support equipment, consumables, spare parts, and of course the operating procedures that will be used to guide the users in the operation of our system. Once these critical enablers are in place, we will be ready to transition the system into operational use.
If you're interested in reading further into the topics we covered in this presentation, you may wish to read the corresponding chapters in the texts associated with the course.